Hello, welcome back to Sleep Science. Tonight, we are going to talk about things that are real. Things that have been observed, measured, studied, argued over in peer-reviewed journals and university conference rooms and late-night emails between astronomers who cannot quite agree on what they are looking at. Things that science still cannot fully explain. Not myths, not stories, not speculation dressed up to feel important. Real signals, real objects, real structures in the fabric of space that our best instruments have detected, and our best minds have sat with for years, sometimes decades, and still cannot account for. You are here, which means you are probably ready to rest. And that is good, because these are not things that should frighten you. They are very far away. Most of them are impossibly far away, and whatever they are, whatever they mean, they are not coming for you. They are just out there, doing whatever it is they do, quietly, patiently, completely indifferent to the fact that a small number of humans on a small planet orbiting an ordinary star have noticed them and cannot stop thinking about them. Which, when you think about it, is a strangely peaceful kind of mystery. So let's begin. In October of 2017, something entered our solar system from interstellar space, which sounds like the opening of something dramatic. And in some ways it was. But the way it actually happened was very quiet, the way a lot of remarkable things happen. Someone was looking at data. Someone noticed something odd. And then, slowly, the oddness accumulated until it became impossible to ignore. The discovery was made on October 19th. A telescope in Hawaii called Pan-STARRS-1 was doing what it usually does, which is scanning the sky for near-Earth objects, things that might be on a collision course. The kind of routine work that sounds exciting in theory and is mostly just careful, methodical watching. And in that watching, an astronomer named Robert Werrick noticed something moving across the sky at a speed that did not fit. The speed was wrong. Not just a little wrong, significantly wrong. Objects in our solar system follow predictable paths. They are bound by the sun's gravity. They move in ways that we have understood for centuries, governed by laws that Newton began articulating in the 1680s and that have held up remarkably well ever since. When you see something moving the way objects in our solar system move, you recognize it. And when you see something moving differently, you notice. This was moving differently. The object was tracked backward through its trajectory, which is something astronomers can do when they have enough data points. They can essentially run time in reverse and figure out where something came from. And when they ran this one backward, it did not come from anywhere in our solar system. Its path, projected backward, pointed to a region of space outside, beyond the boundary of the sun's gravitational influence, from somewhere else entirely. It had come from interstellar space, which had never happened before, not in recorded observation, not in any documented case in the history of astronomy. No known natural object had ever been confirmed to have traveled to our solar system from another star system. We had theorized they might exist. We had expected, actually, that if you looked long enough and carefully enough, you would probably find one eventually. The universe is old, and space is full of things moving through it. It seemed statistically reasonable that occasionally one of those things would pass through our neighborhood. But expecting something and actually seeing it for the first time are very different experiences. They named it Oumuamua. The name comes from Hawaiian, roughly translated as a messenger from afar arriving first, or sometimes just scout, which is a beautiful name actually, even if we chose not to read too much into it. It felt right. Something from very far away, arriving ahead of anything else. First of its kind. And it was already leaving when we found it. That is the part that makes this more poignant somehow. By the time we realized what we were looking at, it had already made its closest approach to the sun. It had already swung around and was heading back out of the solar system, moving away from us. We were watching it leave. We barely caught it at all. The world's largest telescopes were pointed at it as quickly as possible. Every instrument that could observe it was directed there. Astronomers who specialize in very different things suddenly had one common subject. And what they found, as the data came in, was strange in ways that compounded on each other. First, the shape. Oumuamua was not shaped like anything we had catalogued before. The data on how its brightness changed as it rotated suggested something elongated. Significantly elongated. The ratio of its length to its width was estimated to be somewhere between 5:1 and 10:1, and possibly more extreme than that. Which means if you took it and laid it down, it would be something like a cigar, or a needle, or, well, something that does not have a great natural analogue in our solar system. Most asteroids are roughly lumpy. Irregular, yes, but not dramatically so. They are not pancake thin or needle long. They have a kind of random bumpiness that makes sense when you understand how they form, from material colliding and sticking together over billions of years. The process of formation naturally produces something roughly chunky. Oumuamua was not roughly chunky. The brightness measurements showed it rotating, tumbling in a way that is called non-principal axis rotation, which essentially means it was not spinning smoothly around one axis, but sort of wobbling, tumbling through space in an irregular way. And as it tumbled, its brightness changed dramatically. The difference between its brightest and dimmest measurements was a factor of about 10. 10 times brighter at certain angles than at others. For comparison, most asteroids we observe show a brightness variation of maybe a factor of 3 when they rotate. Even that is considered unusual. A factor of 10 is remarkable. It implies something that looks very different from different angles, something with a very unusual shape. But the shape, strange as it was not the strangest thing. The strangest thing was what happened to its speed. As Oumuamua moved away from the sun, astronomers tracked it carefully. And what they found was that it was accelerating. Not decelerating, the way it should if gravity were the only force acting on it. Accelerating. Moving faster than the sun's gravity alone could account for. There is a phenomenon called outgassing, where a comet, as it heats up near the sun, releases gas and dust from its surface. This gas, as it jets out, creates a small but measurable thrust. It is essentially a natural rocket. It is how comets develop their tails, and it is also how they sometimes deviate slightly from purely gravitational trajectories. This was the first explanation offered for Oumuamua's extra acceleration. Maybe it was outgassing. Maybe it was a comet we had not recognized as one. But there was a problem. Comets outgas visibly. The process of gas and dust escaping from a heated surface produces a coma, a kind of fuzzy halo around the object, and often a tail. These are observable. Multiple telescopes looked at Oumuamua during this period and saw nothing. No coma, no tail, no dust cloud, no detectable evidence of outgassing whatsoever. If it was outgassing at the rate required to produce the observed acceleration, those telescopes should have seen something. The physics requires it. The acceleration was large enough that the outgassing would have to be substantial. And substantial outgassing is not subtle. So that theory had a problem. Other explanations were proposed. Maybe the brightness variations had been misread. Maybe the shape was not quite what the data suggested. Maybe there was a thin disc shape, like a pancake, rather than a needle, and that could explain some of the peculiarities. Scientists went back and forth through the numbers, testing different models, and none of them fit perfectly. Every proposed natural explanation required some unusual assumption. Every model had a seam where the data did not quite lie flat. Not necessarily impossible, any of them. Not definitively ruled out. But not clean either. Not the kind of explanation that makes you feel like you have understood something. More the kind that makes you feel like you have just moved the mystery around to a different place. And then, in 2018, a paper was published. The paper came from the Harvard-Smithsonian Center for Astrophysics. It was written by Abraham Loeb, who is the chair of Harvard's astronomy department, and a student named Shmuel Bialy. And the paper proposed, in careful and technically rigorous language, that one possible explanation for Oumuamua's anomalous acceleration was that it might be a light sail. Not a natural object at all, but a piece of technology. The word alien appeared nowhere in the paper as a definitive claim. The language was conditional throughout. They were not saying Oumuamua was definitely built by someone. They were saying that if you wanted to account for the acceleration with a thin, flat, light-reflecting object, the physics worked. Solar radiation pressure on something very thin and very wide could theoretically produce the observed motion. And if such an object existed, it could be, in principle, a deliberately manufactured sail designed to travel through space using light as propulsion. The scientific community's response was mixed, to put it gently. Many astronomers pushed back strongly. The paper was criticized for being speculative, for leaping to an extraordinary conclusion when mundane explanations had not been fully exhausted. Critics pointed out that proposing extraterrestrial technology should be, as Carl Sagan used to say, the last hypothesis you consider, not one of the first. There were still natural explanations on the table. Maybe Oumuamua was a kind of object we had simply never encountered before. A new category of interstellar debris with unusual properties. Avi Loeb, as he is known, did not back down. He continued to argue his position. He wrote more about it. He eventually wrote a book, published in 2021, called Extraterrestrial, in which he laid out his reasoning in full. He was careful to frame it as a hypothesis, a scientific possibility, not a proven fact. But he was also unusually direct for an academic in pointing out that the scientific community's reluctance to seriously consider the possibility of artificial origin was itself a kind of bias. That dismissing an explanation because it seems unlikely is not the same as scientifically ruling it out. It was an unusual position for someone of his standing to take, and it made a lot of his colleagues uncomfortable. The debate has not been resolved. There is no consensus. Oumuamua left our solar system and is now somewhere in interstellar space, moving away from us at tens of kilometers per second. We will never catch it. We will never study it more closely than we already have. Whatever it was, the window closed. We watched it leave, and then it was gone. And the data it left behind is still being argued over. What do we actually know, definitively? We know it was real. We know it came from interstellar space. We know it was tumbling in an unusual way. We know its shape was unusual, possibly extreme. We know it accelerated in ways that were not explained by solar gravity or by any detected outgassing. We know none of the natural explanations proposed for it are fully satisfying. Everything else is still, genuinely, open. And the honest thing to say is that the universe is old and vast and full of processes we do not fully understand. It is entirely possible, likely even, that Oumuamua was a natural object of a type we have simply never seen before. Something that formed in a way we have not catalogued, traveling from a star system different enough from ours that the objects it produces are different from ours. It is also worth sitting with the fact that we do not know. Not as a provocation, not as a clue pointing in any particular direction, just as a fact. A genuine scientific fact. The first interstellar object we ever observed remains, in several important respects, unexplained. There is something strangely comforting in that, actually. Not in the uncertainty itself, but in the scale of what we are uncertain about. Something traveled across interstellar space, passed through our neighborhood, and left before we could understand it. The universe is larger and stranger than our current models, and the evidence of that strangeness passed within our reach and kept moving. And you are here. Warm. Somewhere safe. Far from any of it. Let me try to put interstellar space in a way that makes some sense. The boundary of our solar system is not a wall. There is no edge you could point to. But roughly, there is a zone called the heliopause, which is the point where the sun's solar wind, the stream of charged particles it continuously emits, becomes weaker than the pressure of interstellar space. Beyond that point, the sun's direct influence effectively ends. You are no longer, in the most meaningful sense, inside our solar system. You are between the stars. The nearest star to our own, Proxima Centauri, is about 4¼ light-years away. Light, which travels at roughly 300,000 kilometers per second, takes 4¼ years to cover that distance. Nothing we have ever built comes anywhere close to the speed of light. Our fastest spacecraft, Voyager 1, has been traveling since 1977 and has just barely crossed the heliopause. At its current speed, it would take Voyager about 70,000 years to reach Proxima Centauri. 70,000 years. The space between stars is not just large, it is almost incomprehensibly large. It is mostly nothing. Thin, cold, quiet, nearly empty nothing. The odd molecule here, the occasional dust grain there, vast regions of almost perfect emptiness. For something to cross that emptiness and arrive in our solar system, it would have to have been traveling for an enormous amount of time. Oumuamua was estimated to have originated from roughly the direction of the constellation Lyra, possibly from the star Vega, though the calculations here are imprecise. If it came from Vega, it would have been traveling for somewhere around 300,000 years. 300,000 years ago, modern humans had barely dispersed out of Africa. The oldest cave paintings that have survived are less than 100,000 years old. 300,000 years ago, something left a distant star system, or perhaps drifted free in interstellar space from somewhere older still, and began a journey that ended, briefly, when it passed through our solar system in 2017, and a graduate student in Hawaii noticed it was moving wrong. The patience of the universe is difficult to think about for too long. Which is perhaps why, when Oumuamua left, most people sort of let it go. There were papers, there were debates, there were news articles. But there was also, underneath all of it, a kind of quiet understanding that whatever that was, it was now gone, and we would probably never know. And somehow that understanding was not devastating. Just quiet. The way a lot of honest things are quiet. There are now, as of 2026, a small number of confirmed interstellar objects. The second one was found in 2019, a comet called Borisov, which turned out to be much more ordinary and cometary than Oumuamua. It outgassed the way comets outgas. It had a tail. It behaved. In a way, Borisov was reassuring. It said, yes, objects from other star systems do visit ours. And mostly, they look like things we already know. Oumuamua was the exception, the first one. The one that did not look like something we already knew. And it still doesn't. There is a star about 1,500 light-years away from us, in the constellation Cygnus, the Swan. It sits in a part of the sky that was observed very carefully for about 4 years by the Kepler Space Telescope, which was a mission designed to look for planets by watching for the slight dimming that happens when a planet passes in front of its star. The star is formally catalogued as KIC 8462852, but it is almost universally called by its informal name, which is Boyajian star, named after the astronomer Tabitha Boyajian, who led the team that first noticed it was doing something that did not fit. The way it was found is itself a good story. Kepler was producing enormous amounts of data, more than could be carefully analyzed by professional astronomers alone. And so a project was set up called Planet Hunters, which was a citizen science initiative that allowed members of the public to look through Kepler data and flag things that seemed interesting. People who were not astronomers, sitting at home, going through light curves, which are graphs showing how the brightness of a star changes over time. Most light curves are boring. That is not a complaint. It is what you want. A boring light curve means a quiet, stable star. Occasional small dips when planets cross in front. Regular, predictable, understood. KIC 8462852 was not boring. The citizen scientists flagged it repeatedly. They found the light curves confusing, unusual, unlike anything they had seen in the data. They called the star WTF star in early discussions, which was then sanitized to Where's the Flux star. Flux being the technical term for the brightness measurement. Boyajian and her colleagues took notice and began a proper analysis. What they found was this: the star was dimming. Not in the small, regular, predictable way that planets cause dimming. In irregular, dramatic, sometimes gradual, and sometimes abrupt ways that did not match any standard model. In the most extreme events, the star's brightness dropped by as much as 22%. To put that in context, when an Earth-sized planet passes in front of a Sun-like star, it blocks about 0.01% of the star's light. A Jupiter-sized planet, which is enormous, blocks about 1%. A dimming of 22% requires something very, very large. Larger than any planet. Much larger. But it was not just the depth of the dimming, it was the shape of it. When a planet crosses in front of a star, the dimming curve is smooth and symmetrical. The light dims, reaches its minimum, then brightens back in the same curve, like the planet is a perfect disk. Because it is. Planets are spherical. Their silhouettes are circular. The dimming they cause has a predictable shape. Boyajian stars' dimming events were not symmetric. They were not smooth. They had irregular edges. Some dipped more steeply on one side than the other. Some had complex internal structures, multiple local minima within a single event. They looked, in other words, like something irregular was crossing in front of the star. Something not round, something not solid in the usual sense, something complex and changeable. There was also a longer-term dimming. Beyond the individual events, over the period of Kepler's observation, the star seemed to be getting dimmer overall. Gradually, slowly, not dramatically, but measurably. And when astronomers went back to earlier photographic records, observations of this star going back as far as a century, they found hints that the dimming had been going on, or at least occurring on and off, for a very long time. The first and most popular natural explanation was comets. A large swarm of comets, hundreds or possibly thousands of them, broken up and spreading out in a long arc around the star, could potentially block enough light to produce the observed dimming. It is not a clean explanation. The numbers are awkward. The sheer quantity of cometary material required would be unusual. But it was not ruled out. Comets are real. Comet swarms are real. It was at least a physical possibility. Another explanation was dust. Circumstellar dust, clouds of fine particulate matter between us and the star, could scatter and absorb light in ways that might produce irregular dimming. Observations in different wavelengths could test this theory, because dust absorbs certain wavelengths more than others, leaving a signature. Those observations were done, and the results were complicated. Some data suggested the dust explanation had merit. Some suggested it did not fully account for everything. The dimming events came and went. New events were observed after the original Kepler data ended. There were coordinated campaigns of follow-up observation by telescopes around the world, trying to catch new dimming events in real time and study them across multiple wavelengths simultaneously. What emerged was not a clean answer. Each new round of observation added nuance, added data, made the picture more detailed. But more detail did not translate to more certainty. In some ways, it translated to more questions. The longer-term secular dimming, the slow overall fading of the star over time, was harder to explain with a simple comet swarm or a short-lived dust cloud. Whatever was causing it seemed persistent, stable in its instability. There were other proposals over the years. One was the idea of a Dyson sphere, or a partial Dyson sphere, a theoretical megastructure that an advanced civilization might build around a star to harvest its energy. The dimming, in this framing, would be caused by the structure or structures blocking starlight. This was not widely accepted as a scientific hypothesis. It was more of a thought experiment, a way of exploring the edges of possibility. Most researchers were careful to note it as a way of saying, "We do not know," rather than as a genuine contender. What the careful scientific answer actually is today is something like this. The most likely explanation is probably dust. Some combination of dust and possibly cometary material, possibly including some unusual orbital dynamics around the star that distribute this material in ways we have not fully modeled. But the data is still not entirely consistent with any single explanation. There are features of the dimming, particularly the long-term secular trend and the complex internal structure of some events, that are still being studied, still being argued over, still waiting for an explanation that fits all of the observations at once. The star is still there. It is still being watched. Astronomers with access to appropriate telescopes check it regularly. When a new dimming event begins, notifications go out, and telescopes around the world pivot to look. Because it keeps happening. Whatever is going on around KIC 8462852, it has not stopped. It was happening before we looked. It was happening when we looked. And it is still happening now, 1,500 light-years away, the star dimming and brightening in patterns that no one has fully explained. And the scientists watching it are not panicking. They are not alarmed. They are curious. They are patient. They sit with the data and let it tell them what it tells them. And they wait for the day when a new observation or a new model provides the missing piece. There is something admirable in that. The willingness to sit with an open question for years without forcing it to close. The patience required for this kind of science is worth thinking about for a moment. because it is unusual patience. Not the patience of waiting for something you know is coming. The patience of not knowing whether the thing you are waiting for will ever arrive. This is one of the things that sleep science returns to sometimes. This idea that the work of understanding the universe is not a sprint toward answers, but a long, slow, careful accumulation of detail. Most discoveries do not happen in a flash. They happen in the form of a tiny piece of data that does not quite fit, noticed by someone who was paying close enough attention, followed up on slowly, discussed, challenged, refined, and eventually, maybe, understood. The understanding of Boyajian's star, whatever form it eventually takes, will probably happen that way. One careful observation at a time. One model slightly refined. One anomaly accounted for. And then one day, someone will see it, the pattern that explains it all, and the mystery will close. Or maybe it won't close. Maybe it will just get quieter. Maybe we will understand most of it, and the remainder will wait for instruments we have not built yet. Either way, the star is there. The dimming is happening. 1,500 light-years of empty space between us and it. And still the light reaches us, changed in ways we have not explained, carrying information we are still learning to read. And speaking of light that carries information we are still learning to read, there is another category of signal that has been arriving from deep space for almost 20 years now, and that remains, in very fundamental ways, not understood. They are called fast radio bursts. The name is slightly misleading, the way names for new phenomena often are, chosen quickly before anyone fully understood what they were describing. They are called radio because they are detected at radio frequencies, the long wavelength end of the electromagnetic spectrum, the same general region used by your radio, your Wi-Fi, your phone. And they are called fast because they are fast, staggeringly fast. The shortest ones last about a millisecond. 1 millisecond. 1,000th of a second. Less time than it takes you to blink. Less time than it takes a sound to travel 3 feet through the air. In that fraction of a moment, a burst of radio energy arrives from somewhere in the distant universe, passes through the detectors of a radio telescope, and is gone. The first one was discovered in 2007, though not from a live detection. A researcher named Duncan Lorimer and a student named David Narkovic were going through archival data, observations taken by the Parkes Radio Telescope in Australia back in 2001, and they found a burst that had been sitting unnoticed in the data for 6 years. The burst became known as the Lorimer burst, and it was so strange, so unlike anything that had been catalogued before, that for a time people assumed it might be a data artifact, an error, some kind of interference from a terrestrial source. It was not. More bursts followed. As researchers knew what to look for, and as radio telescopes improved, detections accumulated. There are now hundreds of confirmed fast radio bursts, and the number grows steadily as detection capabilities improve. The current count is somewhere in the hundreds for confirmed events, with more candidates being processed. What they are is straightforward in description and bewildering in implication. A very short, very intense burst of radio waves arrives from outside the galaxy, or in some cases from distant galaxies. The energy involved is extraordinary. In that millisecond or so of emission, the source is releasing more energy at radio frequencies than our Sun produces in total across all frequencies over a period of days or weeks. The exact comparison depends on the specific burst and the assumptions made about the source, but the numbers are consistently extraordinary. Something, somewhere, is doing something very energetic. The leading explanation for most fast radio bursts is magnetars. Magnetars are neutron stars, which are already extraordinary objects. When a massive star reaches the end of its life and collapses, the core can compress into a neutron star, an object roughly the size of a city that contains more mass than the Sun. The density is almost beyond description. A sugar cube-sized piece of neutron star material would weigh billions of tons on Earth. Magnetars are neutron stars with unusually intense magnetic fields, stronger than any other known magnetic field in the universe by many orders of magnitude. And sometimes, these magnetic fields do something. They quake. The surface of the magnetar shifts, a process something like a starquake, and in that shifting, energy is released. A flare, a pulse of electromagnetic radiation. In 2020, a fast radio burst was detected from within our own galaxy. This was significant because it was the first FRB for which the source could be identified at all. The source was a magnetar called SGR 1935 plus 2154, and the burst it produced had the characteristics of a fast radio burst. It was weaker than extragalactic FRBs, which makes sense given it was much closer, but structurally similar. The magnetar flare connection had been theoretical, and now there was one confirmed case. But magnetars cannot explain everything. Some fast radio bursts repeat. They come from the same location in the sky over and over. The first known repeating FRB, called FRB 121102, has been detected hundreds of times from the same source. This source has been localized to a dwarf galaxy about 3 billion light-years away. 3 billion. The burst arrives, passes through 3 billion light-years of space and time, and lands in our instruments. The repeating nature is puzzling. A magnetar starquake could produce a burst, but it seems unlikely the same process would produce hundreds of bursts from the same location over years. Something about the mechanism for repeating FRBs seems different from one-off events. They may be a different phenomenon entirely, just superficially similar in how they appear to our instruments. Some repeating FRBs show periodicity. They burst repeatedly, but only during certain windows. They turn on, produce a series of bursts, then go quiet for weeks, then turn back on. FRB 121102 showed hints of a roughly 157-day cycle. Another source, FRB 180916, showed a clear 16-day period. Active for about 4 days, quiet for about 12, active again, in a regular cycle. What causes a periodic cycle in something that produces this kind of energy is a separate question from what causes the bursts themselves. Possibilities include orbital motion, a companion object periodically blocking or focusing emission, or precessional wobble in a neutron star. None of these is confirmed for any specific source. And then there are the non-repeating bursts. One event, gone. Nothing from that location again. Magnetars can explain those more comfortably, if less definitively. A particularly strong quake releases a burst. The surface settles. Maybe another quake comes years or decades later. From our perspective, monitoring the sky intermittently with finite sensitivity, a second event might simply be missed. Or maybe some FRBs come from something else entirely. There are other proposed sources: merging neutron stars, cataclysmic events that are inherently one-time occurrences, cosmic strings, superconducting strings, highly magnetized white dwarfs. The list is long because the problem is hard and the data is limited. Each detection adds information. Each new source localized tells us something. But the underlying physics of what is happening is still, in important ways, under negotiation. What we know with confidence is this: something is out there producing these bursts. multiple somethings, possibly of multiple types. They are real. They are not instrument artifacts. They arrive from billions of light years away. They carry enormous energy. Some of them repeat, some do not. And the detailed mechanisms, the physical process that produces a radio burst lasting milliseconds from something in a distant galaxy, is not yet fully understood. The field is young. Fast radio bursts were not even known to exist 20 years ago. 20 years is not a long time in science, especially in observational astronomy, where the observations themselves accumulate slowly and the theoretical frameworks take even longer to settle. The researchers working on this are patient, and they have good reason to be. The answers, when they come, will probably reshape what we understand about the most extreme objects in the universe. The room feels quiet when you think about all of this, doesn't it? All these signals crossing billions of years of space, arriving in our instruments in fractions of a second, carrying information about things that happened long before our planet formed. The universe was already doing extraordinary things when the Earth was not yet a planet. It was doing them before life existed here to notice. And it is still doing them now. And we are just beginning to have the instruments sensitive enough to catch the faint echoes. That is not frightening. It is just staggering. There is a difference. You are here, still, resting. The signals are there, out in the dark, crossing distances that reduce any human sense of scale to irrelevance. But they do not touch you. They just arrive in radio dishes in South Africa and Australia and Puerto Rico and China, faint and brief. And the computers attached to those dishes notice something flared, and the astronomers get an alert, and the science continues. Quietly, always quietly. But there is another signal, an older one that arrived not in a millisecond, but over 72 seconds, and that has not arrived again in the nearly 5 decades since. And the fact that it has not arrived again is, depending on how you look at it, either the most mundane thing in the world or one of the most haunting. It happened on August 15, 1977. The Big Ear Radio Telescope in Ohio was part of SETI, the search for extraterrestrial intelligence. It was not the most sophisticated telescope ever built. It was not even the largest. But it was patient. It scanned the sky continuously, looking at every point in its observable range, recording what it heard. On that night in August, at 10:16 p.m. Eastern Time, it heard something. The signal lasted 72 seconds, which is not because something was transmitting for exactly 72 seconds. Big Ear did not point directly at specific locations. It scanned, and as the Earth rotated, the sky drifted through its field of view. Any signal from a fixed point in the sky would be heard for about 72 seconds as the telescope's sensitivity window swept across it. So 72 seconds was simply the time it spent in view. But what it heard in those 72 seconds was remarkable. The signal was strong, significantly stronger than the background noise of space. The way the data was recorded was by a computer that converted signal strength into numbers and letters. A blank, flat background became ones. Stronger signals became higher numbers, then letters when the numbers ran out. The data printout for that 72-second window showed, in a column of characters representing the signal across different frequency channels, a sequence that climbed from the background noise to what the character U would represent, which was among the strongest signals the system could record, and then descended back to baseline. It arrived exactly as you would expect a signal from a distant, fixed point in space to arrive, given the geometry of Big Ear's scanning method. The profile, the way the strength built and then fell, matched exactly the theoretical prediction for a point source in the sky. It was, in its technical characteristics, exactly what a deliberately transmitted signal from far away would look like. A few days later, a volunteer astronomer named Jerry Eamon was going through the printout. He read the column. He saw what the signal looked like. And in the margin of the printout, next to that remarkable column of characters, he wrote a single word. Wow! That word has stuck to the signal ever since. The wow signal. It has its own Wikipedia page, its own replicas. The original printout, with Eamon's handwritten note in the margin, has been photographed and shared countless times. It is perhaps the most famous piece of radio astronomy data in history. The frequency of the signal was close to what is called the hydrogen line, a frequency of 1,420 megahertz. The hydrogen line is significant because hydrogen is the most abundant element in the universe, and any civilization attempting to make itself known might logically choose a frequency related to hydrogen as a universal reference point. It is, in theory, the first frequency you might try if you wanted to say, "Here we are." This is the frequency SETI had been specifically monitoring for exactly this reason. The Big Ear telescope pointed back at the same part of the sky many times afterward. Other telescopes have observed that region of the sky. No one has ever detected the wow signal again. Not once. It came. It lasted 72 seconds. And then there was nothing. Jerry Eamon himself, when asked about it over the years, has been careful and honest. He has said repeatedly that the signal was extraordinary, unlike anything else in the data, exactly what you would hope to detect if a deliberate signal was being sent from somewhere. He has also said that he does not know what it was, and that the failure to detect it again makes it very difficult to draw any confident conclusion from it. The explanations that have been seriously proposed include a natural astrophysical source that has not been identified, possibly something variable or transient that happened to be in that region of the sky and was never observed again, a satellite or piece of space debris that was in the right position and reflected a terrestrial radio signal at just the right angle, some kind of instrumental artifact. And of course, the option that no one can definitively rule out, a deliberate signal of non-terrestrial origin. None of these explanations has been confirmed. The satellite and reflection hypothesis was studied and found difficult to make work with the known positions of satellites at the time. The natural source hypothesis is plausible, but requires a source that has not since been identified. The instrumental artifact hypothesis is difficult to reconcile with how precisely the signal matched the theoretical profile of a point source. In 2017, Robert Gray and his colleagues observed the exact coordinates associated with the wow signal, the best estimates of where in the sky Big Ear was pointing when it made the detection, using the most sensitive instruments available. They found nothing. The position was clean, quiet. The 40th anniversary of the wow signal was celebrated, if that is the right word, by the transmission of a message toward those coordinates. A response of sorts, or a greeting, or just a human gesture into the quiet. Whether anything received it is unknown. Whether anything sent the original is unknown. And the 72 seconds sit in the data, exactly as they arrived, unchanged, unexplained. An event so extraordinary that it earned a handwritten note in the margin from a quiet man reviewing a printout at a desk in Ohio 48 years ago. There is something about the wow signal that feels different from the other mysteries. The others are ongoing, still being observed, still accumulating data. Boyajian's star is still dimming. Fast radio bursts are still arriving. Oumuamua is gone, but at least it was observed extensively while it was here. The wow signal lasted 72 seconds and then stopped. And the stopping is, in some ways, the thing you keep coming back to. If it was a mistake, a glitch, a piece of debris, there would probably have been some sign, some inconsistency in the signal structure. If it was a natural astronomical phenomenon, it should be possible to identify a source, or at least a category of source. And if it was something else, well, if it was something else, then the silence since 1977 is either because the signal was not directed at us and we just happened to intercept it at that angle, like catching one frame of a film, or because whatever was transmitting stopped, or because it moved, or because 47 years of listening have simply not been enough. The silence does not answer the question. Silence never does. It just sits there, on top of the mystery, pressing gently down. But it is a quiet silence, not a frightening one, just the quiet of a frequency that is not currently occupied, a channel tuned to a signal that has not come back. And there is a kind of patience in that too. The frequency is still there, the channel is still open. Big Ear itself no longer exists. It was demolished in 1998 to make way for a golf course, which feels like a detail from a story about priorities. But other telescopes are listening. Better ones, more sensitive ones. The silence has been monitored by instruments that would not have missed much. And still, nothing. But the wow signal, as strange as it is, happened in a specific place, a specific direction in the sky. A single event, 72 seconds long, located somewhere in the general direction of the constellation Sagittarius, though the precise coordinates have been debated because Big Ear had 2 feed horns, and the exact position depends on which one detected the signal. What I want to tell you about next is something that does not happen in a direction, something that is a condition of the universe itself, an anomaly not in a signal or a moving object, but in the oldest light we can see. You may have heard of the cosmic microwave background. If you have not, here is what it is. When the universe was very young, roughly 380,000 years after the Big Bang, it cooled enough for atoms to form. Before that point, the universe was a plasma, a hot, dense soup of particles so energetic that light could not travel freely through it. When atoms formed, the universe became transparent, and all the light that had been trapped in that plasma was suddenly free to travel. And it has been traveling ever since. 14 billion years of traveling. That light is still reaching us today. It arrives from every direction in the sky, uniformly, a faint glow at microwave frequencies that is the oldest light in the observable universe. It has been redshifted by the expansion of the universe from its original higher frequencies down to the microwave range, which is why we call it the cosmic microwave background, the CMB. It was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, who thought at first that the faint noise they could not get rid of in their antenna was being caused by pigeons nesting in the equipment. They shooed the pigeons. They cleaned the pigeon droppings. The noise remained. Eventually they realized it was the oldest light in the universe, and they won the Nobel Prize for it. The CMB is extraordinary for many reasons, but one of the most extraordinary things about it is how uniform it is. In every direction you look, the temperature of the CMB is almost exactly the same. 2.725 degrees above absolute zero, give or take tiny fractions. The universe, on its largest scales, is remarkably smooth. This uniformity is actually a puzzle in its own right, part of what motivated the theory of cosmic inflation, the idea that the very early universe went through a period of extremely rapid expansion that smoothed everything out. But almost uniform is not the same as perfectly uniform. There are tiny variations in the CMB temperature, slightly hotter regions and slightly cooler regions, fluctuations of about 1 part in 100,000. These tiny variations are actually important. They represent the seeds of structure in the universe, the slight overdensities that eventually grew through gravity into galaxies and galaxy clusters. These variations were mapped in extraordinary detail by satellites like COBE, WMAP, and Planck. The maps they produced are among the most scrutinized datasets in all of science. Every tiny ripple in the CMB temperature has been pored over, analyzed, and used to test models of cosmology. And in those maps, there is something wrong. In the direction of the constellation Eridanus, in the southern sky, there is a region of the CMB that is significantly colder than the surrounding area. Not just slightly, significantly. The temperature difference is not huge in absolute terms, roughly 70 microkelvins colder than the average, but it is enough to be statistically remarkable given the uniformity of everything around it. The region is sometimes called the CMB cold spot, or simply the cold spot. The thing about the cold spot that makes it genuinely puzzling is its size. It is enormous, about 1.8 billion light-years across. That number does not pass easily in human terms. Let me try a different approach. The observable universe is about 93 billion light-years in diameter. The cold spot covers a significant fraction of even that vast scale. It is a feature of the universe, not a feature of a galaxy or a galaxy cluster. It is a feature of the whole. The first question scientists asked about the cold spot was whether it was real or whether it was an artifact of the data, some systematic error in the measurement. This is always the first question with an anomaly, and it is the right question to ask. The answer, after extensive analysis by multiple independent teams using different methods, is that the cold spot appears to be real. It shows up consistently in different analyses of the WMAP and Planck data. It is probably not a mistake. The second question was what could cause it. The most mundane explanation, and the one that gained traction, is the supervoid theory. A supervoid is exactly what it sounds like: a region of space that is unusually empty. Not empty like interstellar space, which is already very sparse, but emptier than average on cosmic scales. Regions of below-average matter density. When light from the CMB passes through a region of below-average density, it loses a tiny bit of energy, in a process related to something called the integrated Sachs-Wolf effect. The energy loss makes the light slightly cooler by the time it reaches us. If there were a very large supervoid in the direction of the cold spot, it could potentially cool the CMB light passing through it and produce the observed anomaly. In 2015, a team of astronomers studying the distribution of galaxies found what appeared to be a supervoid in the right direction. A region about 1.8 billion light-years across, with a lower-than-average density of galaxies. The timing and location seemed to fit. But when the physics was worked through carefully, the supervoid, as measured, does not produce enough cooling to fully account for the cold spot. The supervoid is real, but it seems to be only part of the answer at best. The cold spot is colder than the supervoid alone can explain, by a significant enough margin that researchers are not satisfied that the mystery is solved, which brought other explanations back into the conversation. One of the more unusual proposals is that the cold spot might be evidence of a collision between our universe and another. This sits within the framework of the multiverse, the idea that our universe is one of many, each with its own properties, each potentially beginning in its own Big Bang-like event. If two universes had been close enough to interact, to brush against each other in whatever sense that might mean, the collision might have left a thermal imprint on our CMB. A bruise. A mark in the oldest light we can see, showing where the boundary between our universe and another was, once, long ago. This hypothesis is genuinely scientific in the sense that it makes predictions. If it were true, you would expect the cold spot to show certain patterns, to have a specific profile of temperature variation. Whether those predictions match the observations is still being worked out, and the verdict so far is that the match is not obviously clean, but also not obviously ruled out. Most cosmologists would probably say the supervoid explanation, perhaps combined with some statistical rarity in the early universe's fluctuations, is the more likely answer. The multiverse collision is a long way from confirmed, but it has not been ruled out. And the fact that it is even on the table, that a real anomaly in real data, has led serious scientists to seriously consider whether we might be seeing evidence of another universe, is a measure of how strange the cold spot actually is. The universe left a mark on itself. We found it. We do not fully know what made it. That seems like the kind of thing that should feel more momentous than it does. But maybe the quietness is appropriate. It happened 14 billion years ago. Whatever caused it is long gone, or very far away, or is simply a property of the universe we happen to live in. It is just there, in the data, in the oldest light, waiting for someone to understand it. And then there is the thing that is not a signal and not an object, but is a gravitational fact. A pull. Something that is moving our galaxy, and millions of other galaxies, toward a point in space that we cannot directly see. We call it the Great Attractor. But that will have to wait just a moment, because first I want to stay with the cold spot a little longer. With this image of standing at your instruments and finding something in the oldest light in the universe that does not fit. Because there is something about the scale of that kind of mystery that I think deserves to be felt, not just understood. 380,000 years after the Big Bang, the universe becomes transparent. Light pours outward in every direction. For 14 billion years, that light travels. It loses energy as the universe expands. By the time it reaches us, it is cold and faint and ancient beyond our ability to really comprehend. And somewhere in that ancient, uniform glow, there is a scar. A region that is slightly colder, slightly emptier, inexplicably so, given everything we know about how the CMB should look. Something happened there. Long before the sun existed, long before the Milky Way had taken its current shape. In the very early universe, or perhaps on the boundary between our universe and something outside it, something happened that left a mark that we can still read today with the right instruments. This is sleep science, and this is what we do here sometimes. We sit with the scale of these things, not because it should overwhelm you, but because it is real. The universe has been here for a long time, doing things, leaving marks, and we are very new arrivals who are only just beginning to have the tools to read what it has written. And there is something peaceful in that, genuinely peaceful. Not the manufactured peace of being told everything will be fine, the real peace of being small and safe and curious, sitting with questions that are too large for any one mind to hold, and finding that the largeness is beautiful rather than threatening. The cold spot sits in the data. The wow signal sits in the old printout in Ohio. Boyajian's star dims and brightens 1,500 light-years away. Fast radio bursts arrive in fractions of seconds from billions of light-years distant. And Oumuamua is somewhere in the dark between the stars, tumbling, moving, carrying whatever it is made of and whatever it means towards some destination neither it nor we will ever know. All of these things are happening, or have happened, or are still arriving, the light of them crossing space, not yet here. And none of them are here. None of them are close. They are out there, in the dark, in the old silence between galaxies, doing whatever they do, indifferent and patient. And you are here, in a room, soft and still. And the distance between you and all of those things is incomprehensibly, mercifully vast. Now, the Great Attractor. The name is perhaps a little dramatic. It was coined in the late 1970s and 1980s when astronomers began to notice something odd about the motions of galaxies in our part of the universe. Galaxies are not stationary. The universe expands, which means that on average, distant galaxies are moving away from us. The further away, the faster they recede. This is called the Hubble flow, and it is one of the foundational observations of modern cosmology. But galaxies also have their own individual motions, called peculiar velocities, layered on top of the Hubble flow. In the 1970s, astronomers studying the peculiar velocities of galaxies in our local region of space began to notice something. Our galaxy, the Milky Way, and many of the galaxies around us were not moving purely with the Hubble flow. They were being pulled, moving toward a specific region of the sky, in the direction of the constellations Centaurus and Norma, with a velocity that could not be explained by any visible matter in that direction. The motion was coherent. Thousands of galaxies, spread across hundreds of millions of light years, all drifting in roughly the same direction. This is called a bulk flow, a large-scale streaming motion of galaxies. And the thing they seemed to be streaming toward was eventually named the Great Attractor, because it was attracting things, gravitationally, on a grand scale. The problem with studying it was immediate and persistent. It is in the wrong direction. From our vantage point in the Milky Way, the Great Attractor lies almost exactly in the plane of the galactic disk. And the galactic disk is full of gas and dust. When you look in that direction, you are looking through the densest, most obscuring part of our own galaxy. Stars and their light are behind layers of interstellar material, entire star-forming regions, nebulae, dense clouds of molecular gas. Everything in that direction is obscured. Astronomers call this the zone of avoidance, which is not a dramatic name for dramatic reasons. It is just a practical description. There is a band across the sky where the Milky Way itself blocks our view of what lies beyond. And for decades, it was exactly the zone you had to avoid when trying to see the distant universe, because you simply could not see through it. The Great Attractor is sitting behind the zone of avoidance. Instruments that can see through dust have helped. X-ray telescopes, which detect radiation that passes more easily through galactic disk. Dust. Radio telescopes, which observe at frequencies where dust is more transparent. Infrared surveys that can peer through material that blocks visible light. These have helped astronomers map the region around the Great Attractor with increasing precision. What they found over time was a large concentration of galaxies, a supercluster of galaxies and galaxy clusters, a region of above-average mass density, centered in the approximate direction of the Great Attractor. This structure, sometimes called the Norma cluster or the Norma supercluster, or occasionally the Great Attractor itself, is a real and massive concentration of matter. It is located roughly 150 to 250 million light-years from us. It is attracting us, along with all the other galaxies in our local region, the way any massive concentration of matter attracts things: gravity. This explanation is real. The Great Attractor is, in important ways, understood. It is a gravitational overdensity, a concentration of mass. This is satisfying as far as it goes, but there are complications. The motion of our local group of galaxies toward the Great Attractor is not fully explained by the Norma supercluster alone. The flow continues. When you measure the peculiar velocities of galaxies very carefully and trace where they are all ultimately heading, the picture gets larger. Beyond the Great Attractor, there is an even larger structure called the Shapley supercluster, one of the most massive concentrations of matter in the nearby universe, located about 650 million light-years away. The Shapley supercluster might be doing more of the gravitational work than the Great Attractor, or both might be contributing. The analysis depends on careful measurements and modeling that is ongoing. And behind even Shapley, in the larger scale surveys of galaxy motion, there are hints of even larger structures. The universe has a sort of texture, a foam-like pattern of filaments and voids and nodes, and the nodes, where the filaments intersect, are where the largest concentrations of mass sit. Our local region is being tugged from multiple directions and distances by this overall structure. The exact contribution of each piece to the bulk flow we observe is still being worked out. The Great Attractor as a concept, as a single thing pulling us in one direction, is somewhat simplified. The reality is a web of gravitational influences, some closer, some further, some still only partially mapped because we are trying to see through our own galaxy to find them. There is also a deeper question, which is whether there is something even beyond the Shapley supercluster contributing to the bulk flow. Some analyses of very large-scale peculiar velocities have suggested the flow might be coherent on scales even larger than Shapley, pointing towards something even further away. Other analyses disagree. The data at these scales is difficult to obtain and interpret. This is the frontier of the research, not settled, not a closed question. The Great Attractor has been partially explained, but the full accounting of what is pulling on us, and how much, and from how far, is still being written. Our galaxy is moving. It has been moving for billions of years. It will continue to move. And the thing, or things, that are pulling it are partly understood and partly still behind the dust, behind the distance, behind the limitations of what our instruments can currently see. I keep coming back to what it means that these things exist. Not what they imply about other civilizations, or about physics, or about cosmology. Just the bare fact of them. That we are here, on this planet, and we have built instruments sensitive enough to detect a radio signal 72 seconds long from possibly interstellar space. That we have built telescopes that can measure the temperature of the oldest light in the universe to within millionths of a degree, and find an anomaly the size of nearly 2 billion light-years. That we have tracked a small tumbling object through our solar system, found that it came from between the stars, and noticed that it was moving in ways that did not fit our models. The sophistication required to notice these things is extraordinary. The sensitivity required to measure them is extraordinary. And yet, even with all of that, the answers remain open. Which is not a failure. This is worth saying clearly. The open questions are not evidence that the instruments were inadequate or the scientists were not clever enough. The open questions are evidence that the universe is genuinely, structurally, more complex than any model we have yet built. The mysteries are not holes in our knowledge. They are the correct shape of our knowledge, the places where the surface of what we understand borders the infinite amount we do not. There are people who spend their entire careers on one of these questions. Tabitha Boyajian has devoted years to that star, collecting observations, organizing follow-up campaigns, sitting with data that has not yet given up its secret. The astronomers who study fast radio bursts have built new instruments specifically to catch more of them, to detect them in real time rather than in archival data, to localize them to their host galaxies so the environment can be studied. Jerry Eman, who wrote "Wow" in the margin of a printout, spent years doing careful analysis of what that signal was and was not. He was methodical and honest about the limits of what one detection, never repeated, could tell anyone. The scientists who work on the cold spot run the data again with each new generation of CMB satellite, each better map, checking whether the anomaly holds up, what its precise properties are, whether any new explanation emerges from the improved measurements. This work is quiet. It does not always make the news. It does not usually make the news. It is the work of careful people sitting with hard problems for a long time, not demanding answers on a human schedule, not giving up when the answer does not come quickly. There is something in that which feels worth saying at this particular hour. The people who try to understand the universe do not need the universe to yield quickly. They are patient with it. They know that the universe is older than any question they can ask about it, and that the answers, when they come, will come in the universe's time, not theirs. And while those careful people watch their instruments and process their data and write their careful papers, the things themselves continue. Boyajian's star dims. Another few percent. Another irregular event. The automated alerts go out. The telescopes pivot. The observations accumulate. Somewhere in the distant universe, a fast radio burst fires into space. A millisecond. A burst of energy. Crossing 1 billion light-years. Arriving eventually in the field of a radio telescope that was pointed in exactly the right direction at exactly the right moment. And the CMB, the oldest light, continues its journey through the universe. Faint, ancient, carrying the memory of what the universe was like when it was young, including that one region that is slightly colder than everything around it, that has waited in the data for someone to explain it, and is still waiting. And somewhere in intergalactic space, further than any of this, the structure of the universe continues its slow gravitational dance. Filaments of matter spanning hundreds of millions of light-years. Voids almost empty of galaxies stretching further. And at the nodes, concentrations of mass pulling everything nearby toward them, including this galaxy, this ordinary barred spiral with its hundreds of billions of stars, one of which is the Sun, around which there is a small rocky planet on which the patient scientists sit with their instruments and their open questions. The Great Attractor will not reach us. That is not how gravity works on these scales. We are falling toward it the way the Earth falls toward the Sun, in orbit, in a kind of endless approach that is also an endless circling. The universe expands even as gravity pulls locally. We drift and fall and drift, and the distances involved are so vast that none of this motion matters on any timescale a human life touches. But it is happening. Every day, every moment. The galaxy is moving. The light of distant stars is aging. The cold spot is there, in the ancient glow, unchanged. The frequency of the wow signal is available, open, waiting. The coordinates where it came from are observable tonight, if you had the right equipment and pointed it at the right patch of sky between Sagittarius and Aquila. Somebody might be pointing there right now. Some telescope somewhere, in its automated nightly survey, passing its sensitivity window over that region of sky, listening, hearing nothing, or hearing something. We would not necessarily know immediately. Data takes time to process. Events get flagged and reviewed. The pipeline from raw observation to confirmed detection has many steps. The second wow signal, if it ever comes, might already be sitting in a data file somewhere, waiting for someone to look at the right column at the right time and notice that the numbers climbed where they should not have climbed. These things are so far away that the word far stops working. The wow signal came from at least several hundred light years away, possibly much further. The fast radio bursts come from billions of light years. The cold spot is a feature of the whole observable universe. The Great Attractor is hundreds of millions of light years from here. And Oumuamua is between the stars. Moving, gone from our solar system now for years. If it is natural, it is continuing whatever journey it was on long before we existed, unaffected by having passed through our neighborhood. If it is something else, then the same applies. It did not stop. It did not turn around. It came from wherever it came from, past us, and left in whatever direction it was already heading. The universe does not organize itself around our observations of it. It does not wait for us to understand something before moving on to the next thing. It has been doing extraordinary, strange, and partly inexplicable things for 13.8 billion years, and it will continue doing them whether we are watching or not, whether we understand or not, whether we ask the right questions or the wrong ones, or no questions at all. Which is not melancholy. At least, it does not have to be. There is something else in it, something that feels more like privilege than like loss. We are the part of the universe that has managed to notice the universe. We are the arrangement of matter and energy that has produced instruments sensitive enough to catch a 72-second signal in 1977, or to measure a slight temperature anomaly in light 14 billion years old, or to track an object tumbling through our solar system and notice that its acceleration does not fit. We are, as far as we know, the only thing in the universe that is currently wondering what the universe is. And that, at this hour, in this quiet, is not a burden. It is just true. The researchers who study these mysteries tend, in my experience of reading their work and their interviews, to be characterized by a particular kind of cheerfulness. Not the cheerfulness of people who have found what they were looking for. The cheerfulness of people who are still looking, who like looking, who find the act of looking more interesting than the finding. Tabitha Boyajian has spoken about the years she has spent on KIC 8462852 with a kind of patient affection. Not frustration that it has not yielded its secret, but appreciation for the fact that it is still a question, still worth watching, still doing strange things that require explanation. The mystery is, in some sense, the point. Not because mysteries are comfortable to live with, but because they are honest. They are what reality looks like before the understanding catches up. The fast radio burst researchers are some of the more enthusiastic people in observational astronomy right now. And that energy is not despite the unanswered questions, but partly because of them. The field is new. The detections are improving. Every new burst is another data point, another chance to see something that adds to the picture. The not knowing is not an obstacle. It is the territory they signed up to explore. The cosmologists working on the cold spot, the ones who spend their time running statistical analyses of CMB data and building models of supervoids and checking whether the multiverse hypothesis makes the right predictions, are doing work that may not resolve for decades. The instruments needed to really test some of these ideas do not yet exist. They are working in the knowledge that the answer might come after them, that they are contributing to a conversation that will be continued by people who are not yet scientists, who are maybe not yet born. That is a particular kind of generosity. When I try to think about what connects all of these mysteries, Oumuamua and Boyajian's star, and fast radio bursts, and the wow signal, and the cold spot, and the Great Attractor, I keep coming back to the same idea. Each of them is the universe being honest about its own complexity. Not showing off, not signaling, just being what it is, which turns out to be significantly stranger than the models we built to describe it. Our models are good. They are remarkable, actually. General relativity and quantum mechanics, and the standard model of particle physics, and the standard cosmological model have all been tested to extraordinary precision and held up under enormous scrutiny. We have built real predictive power about the real universe. And then, sometimes the universe does something unexpected, something that falls slightly outside the frame of what the model predicted. And the question becomes, is the model wrong? Or is this a natural but unusual phenomenon within the model that we simply have not catalogued yet? Or is it something new, something the model will need to grow to accommodate? That question, asked quietly and carefully for each anomaly, is the work. And right now, for each of these mysteries, the work is ongoing. The models are not broken, but they are being tested, and somewhere in the data, the answers are present, waiting for the right instrument, or the right analysis, or the right moment of insight to become visible. There are nights when the sky is very clear, and you can see the Milky Way as a band of light, and it is possible, just barely, to feel the scale of it. The hundreds of billions of stars, the vast disk of the galaxy. And somehow, on those nights, the scale does not crush you. It just sits there, being what it is, and you sit there, being what you are. And the ratio between you and the galaxy is so extreme that the feeling it produces is not despair, but something closer to peace. Because the scale does not change what you are. You are still here, still warm, still thinking, still a thing that can notice the Milky Way and feel something about it. And that noticing, that capacity to find the universe strange and beautiful and worthy of attention, is rarer than any of the mysteries we have talked about tonight. As far as we know, there are very few places in the universe where that kind of noticing happens. Possibly just here. Possibly many places we have not found. But wherever it happens, it is the universe looking at itself. The matter and energy of the cosmos organized in such a way as to wonder at the cosmos. And tonight, in this quiet, that is what is happening. You are listening. The universe is out there, doing its unexplained things, leaving its strange marks in data and light curves and old radio printouts. And between you and all of that is this moment. This warm, still, almost sleeping moment. The Great Attractor is pulling the galaxy toward it. The pull is real, continuous, happening at this moment. But it would take tens of millions of years for us to get meaningfully closer to it, and even then we would not arrive. We would drift and curve, and the universe would expand, and the whole thing would continue exactly as it has been continuing. You have time. More than enough time. And there is something else. Something that does not get said enough in discussions of the unexplained, which is that the unexplained is not a problem with reality. It is a property of reality. The universe is the kind of place that can produce things that exceed our current ability to explain them. That is not a failure. That is a fact about the universe's relationship to our understanding. The universe is older and larger and more complex than any model of it, and we should expect, periodically, to encounter things that fall outside the edges of the map. The edges of the map are not the end of the world. They are the beginning of the next question. Oumuamua was the edge of the map. Whatever it was, it came from beyond what we had catalogued, and behaved in ways our models did not fully predict, and left before we could understand it. That edge, in the form of archived data and ongoing debate and the occasional new paper, is still there to be explored. Boyajian's star is the edge of the map. Something is happening around that star that our best models of stellar physics and planetary formation and circumstellar dust do not entirely account for. The edge is open, and every new observation either pulls the boundary a little closer to understanding or reveals that the territory is even stranger than it appeared. The wow signal is perhaps the sharpest edge of all. One detection, no repetition, no confirmed source. A 72-second event in 1977 that matched, in its technical characteristics, exactly what you would expect if someone, somewhere, was trying to be heard. And then nothing. The edge does not move. It just stays there, in the old data, unexplained and unextended. The cold spot in the CMB is an edge that is 1.8 billion light-years wide. The universe's own ancient record has something in it that does not fully fit. A region that is colder than it should be, that might be the fingerprint of a supervoid, or might be something else, or might be both, or might be the scar of a contact between our universe and whatever lies, if anything lies, beyond it. When you let that idea settle, really settle, the universe is not just strange. It is strange in a way that points outward, past itself, to the possibility of other universes, other something or nothings, beyond the boundary of what we can observe. And that boundary is not a wall, it is a horizon. The horizon of the observable universe, defined simply by how far light has been able to travel in the time the universe has existed. Beyond it, there may be more universe. There probably is. And further still, there may be things that our physics does not describe, things that our physics cannot describe, because they are outside the system that generated our physics. This is where cosmology touches philosophy. Not because the science becomes less rigorous, but because the questions become so fundamental that they cannot be answered by observation alone. You cannot observe beyond the observable universe. You cannot test what lies outside the system. You can only look at what is here, in the observable, and notice the marks it has left, like the cold spot, and ask what they tell you about what might be out there. The answer, right now, is that they tell you something is possible. Something is consistent with certain models of what might exist beyond the horizon. And the rest is mathematics and patience and waiting for better data or better theory or a new idea that nobody has had yet. Somewhere in a university office, someone has a printed copy of a CMB temperature map pinned to their wall. Marked on it, in one region of the southern sky, is a circle, roughly drawn, indicating the cold spot. They have been looking at that circle for years. They have run analyses that seemed to explain it, found the explanations incomplete, revised, reconsidered. They are patient with it. The circle is patient too. It will be there next year, the year after. It will still be in the data when those researchers retire and someone younger takes up the question. The cold spot has been in the CMB for 14 billion years. It will wait. And out in the direction of Centaurus and Norma, beyond the dense plain of the Milky Way, beyond the zone of avoidance, the Norma supercluster sits. Massive, dense, pulling everything in its gravitational sphere toward it with the slow, patient inevitability of mass. Our galaxy is falling toward it in the way a leaf falls on still water. Slowly, continuously, without noticing. Hundreds of millions of years from now, the Milky Way will be somewhat closer. And the Andromeda Galaxy, which is also falling toward the Great Attractor along its own path, will be much closer still, approaching a merger with the Milky Way that is already predicted and already beginning. When Andromeda and the Milky Way eventually collide and merge, in about 4.5 billion years, the resulting galaxy will have its own trajectory, its own fall toward the massive concentrations of matter in this part of the cosmos. All of this is known, predicted. The physics is settled. The Great Attractor is pulling us. Andromeda is coming. The sun will eventually exhaust its hydrogen. These things are not mysteries. But alongside them, embedded in the same universe, are the things that are mysteries. Oumuamua's acceleration, Boyajian's dimming, the wow signal's silence, the cold spot's depth. The things that fall outside the frame of what the model cleanly predicts. The universe is mostly explicable, and the unexplained corners of it are not cracks in the foundation. They are the places where the foundation might be extended, deepened, rebuilt with better materials. The places where the next great understanding might be waiting. It is getting late, or early, depending on where you are in the night. The sky outside, if you could see it, if the lights were off and the air were clear, would be full of light that has been traveling for years, for centuries, for millions of years. Every star you can see is not where you are seeing it. You are seeing where it was when the light left. The light travels, and the star moves, and by the time the light reaches you, the star is somewhere else. Everything in the night sky is history. Everything is late news from somewhere far away. And embedded in that ancient light, arriving alongside the photons from nearby stars, are the signals from further. The fast radio bursts, lost in frequencies your eyes cannot see. The CMB itself, bathing the Earth from every direction, faint and ancient, the oldest message in the universe, saying only, there was a beginning, and it was hot, and there was a cold spot, and we do not know why. The cold spot sits in the data like a question that has been asked but not answered. And the strange thing about that, the thing that takes a moment to settle, is that the question is not new. It has been there for 14 billion years. We have only been asking it for about 20. 20 years of asking. 14 billion years of waiting to be asked. Now, the Great Attractor. We touched on it briefly before, but I want to come back to it, sit with it properly, because it is one of those things that rewards attention. The more carefully you look at it, the stranger and more interesting it becomes. The name arrived before the understanding did. Astronomers in the late 1970s and early 1980s were doing careful surveys of galaxy motions in our local universe. They were measuring what are called peculiar velocities, the motion of galaxies above and beyond what the general expansion of the universe would predict. And they kept finding the same thing. Our galaxy, and the galaxies around us, and the galaxies around those, were all drifting. Not randomly, together, in a coherent flow, toward a region of the sky in the direction of the constellations Centaurus and Norma. Something was pulling, something massive enough to create a gravitational current felt across hundreds of millions of light years. They called it the Great Attractor, and for a time it had a genuinely mysterious quality to it. This invisible gravitational presence behind the dust of our own galaxy, pulling at us, pulling at everything nearby, and impossible to see directly because the Milky Way was in the way. The zone of avoidance. That band across the sky where our own galaxy blocks the view of the distant universe, where the density of dust and gas is so high that optical telescopes see almost nothing of what lies beyond. And the Great Attractor, with almost comedic inconvenience, was sitting almost perfectly behind it. X-ray telescopes helped. Infrared surveys helped. Radio observations helped. Slowly, through instruments that could pierce the dust, the region behind the veil became clearer. What emerged was the Norma cluster, a dense concentration of galaxies and galaxy clusters, a significant gravitational mass located roughly 150 to 250 million light-years from us. And the Norma cluster is real. The mass is real. The gravitational pull is real. In that sense, the Great Attractor is not a mystery in the same way the wow signal is a mystery. We know what it is, broadly. A gravitational overdensity. A concentration of matter that is doing what concentrated matter does, which is pull things toward it. But the details are not fully settled. The motion of our local group of galaxies is more complex than a simple fall toward the Norma cluster. When researchers study the bulk flow very carefully, accounting for the contribution of all the mass they can map, there is still something left over. The flow is larger, more coherent, over larger distances than the Norma cluster alone fully accounts for. Beyond the Great Attractor lies the Shapley supercluster. Located about 650 million light-years away, it is one of the most massive concentrations of matter in the nearby universe. A supercluster of superclusters. Its gravitational contribution to the bulk flow we observe is significant, possibly more significant than the Norma cluster's contribution. So the simple picture, the single named attractor pulling everything toward it, is somewhat misleading. The reality is a hierarchy of gravitational influences. Local clusters pulling on us, superclusters beyond them. The web of large-scale structure, the filaments and voids and nodes that characterize the universe on its largest scales, all contributing to the net pull felt by our galaxy and everything around it. We are embedded in a gravitational landscape, moving through it, shaped by it. The Milky Way's trajectory through the universe is the result of all of these forces, accumulated over billions of years, pointing us in a particular direction at a particular speed. And the full mapping of that landscape, the accounting of all the mass that contributes to all the motion we observe, is still ongoing, still being refined. New surveys of galaxy positions and velocities add data. New analyses find contributions from structures even further away. The picture grows larger with each generation of observations. What remains genuinely uncertain is whether the bulk flow, the large-scale streaming of galaxies in our region, is fully explained by the visible matter we have been able to map. Some analyses suggest it might not be. That there may be contributions from structures so distant they are near the edge of the observable universe, or that the distribution of dark matter, which does not emit light and can only be inferred from its gravitational effects, plays a role that is not yet fully accounted for. Dark matter is present in enormous quantities throughout the universe. It is estimated to make up about 27% of the total mass-energy content of the cosmos, compared to about 5% for ordinary matter, the kind that makes up stars and planets and you. Its distribution is not uniform. It clumps around galaxies and galaxy clusters. It forms an invisible web that ordinary matter follows. And understanding its distribution in the region around the Great Attractor is part of understanding the gravitational landscape we are moving through. The Great Attractor, in the end, is not one thing. It is a region, a gravitational environment, a complex superposition of masses at different distances, all contributing to a net pull that has been shaping the motions of galaxies for billions of years. We have explained a great deal of it, and a smaller but still genuine portion of it is still being worked out. What I find myself thinking about, sitting with all of these mysteries together, is not what they might mean for our understanding of physics or cosmology in the abstract. I find myself thinking about the people who discovered these things, who sat with the data and found something wrong in it, something unexpected, something that did not fit. and who then had to decide what to do with that finding. Robert Weirich, processing Pan-STARRS data and noticing an object moving at the wrong speed for a solar system object. Jerry Eman, going through a printout and finding a column of numbers that climbed impossibly high, and reaching for a pen and writing one word. The Planet Hunters volunteers, sitting at home at their computers, going through light curves for a star 1,500 light-years away, finding one that made no sense, flagging it again. Duncan Lorimer and his student, going through archival data from a radio telescope in Australia, finding a burst of radio energy from 2001 that had been sitting in the files unnoticed for 6 years. Tabitha Boyajian and her team, staring at the data from KIC 8462852, trying explanation after explanation, finding each one incomplete. These moments have a particular texture to them. The moment before you understand what you are looking at. When the data is in front of you and something is clearly wrong, clearly unusual, and you do not yet know what it means, or whether it is real, or whether it will hold up under scrutiny. There is a very specific feeling in that moment, and the scientists who experience it describe it in similar ways. A kind of suspended disbelief, a reluctance to believe what you are seeing because it is too unusual. And then, slowly, the reluctance giving way to the seriousness of the thing, the need to check and recheck, to make sure it is not an error, to find out whether it is real. It is almost always real. The instrumentation does make errors sometimes. Data artifacts are real. Interference from terrestrial sources is real. But the things that survive careful checking, the anomalies that hold up under scrutiny and replication and independent analysis, are real. Oumuamua was real. The wow signal was real. The cold spot is real. Boyajian stars dimming is real. The fast radio bursts are real. And each of those discoveries began with someone noticing something wrong in a way that turned out to be right. The patience of the work extends beyond the individual scientists. It extends into the instruments themselves. Radio telescopes pointed at the same regions of sky, year after year, decade after decade. The cosmic microwave background satellite data processed and reprocessed with each new generation of analysis tools. The Kepler Space Telescope, which ran for 9 years before its fuel was exhausted, staring at the same patch of sky, collecting the brightness measurements of 150,000 stars, accumulating an archive that researchers are still mining. Kepler is gone now, retired. But its data still lives, and researchers still find things in it. New planet candidates, new stellar variability, possibly new mysteries hiding in the numbers, waiting for someone to look in the right way. The successor missions carry on. The TESS satellite, watching wider patches of sky. The James Webb Space Telescope, observing the universe in infrared with a sensitivity that makes previous instruments look myopic. New radio arrays, more sensitive than anything that existed when Jerry Eman wrote his single word in a margin. The instruments get better, the data accumulates, and somewhere in the growing archive, the answers to some of these questions are probably already present, waiting not for new observations, but for the right analysis, the right eyes on the right data at the right moment. There is a concept in science called the streetlight effect, named after the old joke about someone looking for lost keys under a streetlight, not because that is where they lost them, but because that is where the light is. The idea is that scientists, like everyone else, tend to look where it is easy to look, where the instruments are pointed, where the methods work well. And the things that are genuinely strange and new are often not where the streetlight falls. Oumuamua was found because the Pan-STARRS telescope happened to be sweeping the right area of sky at the right time, as an object that had come from interstellar space passed through our neighborhood. We were lucky. If it had arrived at a slightly different angle, or if the survey had not been running when it did, it would have come and gone undetected. We might have missed it entirely. How many interstellar objects have passed through the solar system undetected? How many fast radio bursts have arrived at frequencies or from directions not covered by the telescopes that were operating at the time? How many events like the WOW signal have occurred, in other frequency ranges or in parts of the sky not observed by Big Ear in 1977? We do not know. By definition, we cannot know. The things we have not detected are invisible to us precisely because we have not detected them. But the instruments are improving. The sky coverage is increasing. The sensitivity thresholds are dropping. And as the street light gets brighter and covers more ground, things that were in the dark start to become visible. The next Oumuamua will probably be detected faster, with better instruments, and studied more thoroughly before it leaves. Assuming the next one is within reach, assuming we are watching the right patch of sky at the right time. There is no guarantee, but the odds improve with each new telescope, each new survey, each improvement in the pipelines that process the data. The Rubin Observatory, now operational, is conducting the Legacy Survey of Space and Time, a 10-year program that will observe the entire visible sky every few nights with a camera of extraordinary sensitivity. It is expected to detect many new interstellar objects, possibly dozens over the course of the survey. The era of Oumuamua being uniquely strange may give way to an era where we have a population of interstellar visitors to study, compare, categorize. And maybe in that population, most will be like Borisov, recognizably cometary, behaving as expected. And maybe one or two will be like Oumuamua, refusing to fit neatly into any known category, demanding a new explanation. Or maybe we will find that Oumuamua, looked at in the context of a larger sample, makes more sense. That there is a natural population of objects that look like it, shaped by processes we had not previously considered, and that it was only strange because it was the first. That would be satisfying in its own way. Not as dramatic as the alternative, perhaps, but deeply satisfying. The mystery would close, and in closing, it would open the door to a new understanding of what kinds of things travel between the stars. The resolution of a mystery is not always what you expected. The resolution of the mystery of the Milky Way's position in the universe was not dramatic. For a long time, astronomers assumed our galaxy was somewhere ordinary, somewhere average. It turned out we are not quite at the center of anything, which we knew, but also that we sit within a larger structure called the Laniakea supercluster, a vast assembly of galaxy groups and clusters covering about 500 million light-years, roughly 100,000 galaxies, all bound together gravitationally, all falling slowly toward the same attractor region. Laniakea was only defined and named in 2014. The word means immeasurable heaven in Hawaiian. It is the cosmic address of the Milky Way, and understanding it required tracing the flow of galaxy motions, which required mapping the Great Attractor, which required decades of careful observation through and around the zone of avoidance. The mystery of the Great Attractor was not solved by a dramatic discovery. It was solved, partially, by accumulation. By observation after observation, analysis after analysis, the structure behind the dust gradually becoming clear. There is still more to learn, but the shape of the answer is visible. Some mysteries close that way, not with a flash of insight, but with a long, patient accumulation of data until the picture resolves the way a photograph resolves in a darkroom, detail by detail, until you can see what you are looking at. I wonder sometimes what the resolution of the WOW signal would look like, if it ever comes. Maybe a radio telescope in a future decade, more sensitive than anything we currently operate, catches something from the same region of sky. A signal, brief, intense, with the same characteristics. And this time, there are enough facilities watching to triangulate the source, to localize it to a specific star or a specific direction, to study it in multiple wavelengths simultaneously. Or maybe the opposite. Maybe the analysis continues, decade after decade, and gradually the natural explanation becomes clear. A type of astronomical transient not yet fully characterized. Something like a fast radio burst, but at lower frequencies. Something that occurs rarely from certain kinds of stellar environments. And the WOW signal, revisited, fits the profile. Either of those resolutions would be extraordinary in different ways. Or maybe nothing happens. Maybe no signal like it is ever detected again. And the 72 seconds in the 1977 data remain exactly what they are now. An unexplained event with characteristics that match a deliberate transmission, but no evidence sufficient to confirm that reading, and no repetition to settle the question. That would also be a kind of answer. An answer shaped like an open door that no one ever walked through again. The honest acknowledgement of uncertainty is one of the things that makes science beautiful, when you let yourself see it that way. Not the uncertainty itself. Nobody loves uncertainty. But the willingness to say, clearly and without embarrassment, we do not know. Not yet. Maybe not ever. But we are still looking. There is no other system of knowledge that operates this way. No other tradition that treats the admission of ignorance as a prerequisite for progress. In science, the open question is not a weakness. It is the engine. You cannot answer a question you are pretending is already settled. And so the questions stay open. The data stays in the archives. The telescopes stay pointed. The researchers stay at their desks, and their graduate students stay at theirs. And the community of people who care about unexplained things in the sky slowly grows, generation by generation, each one inheriting the open questions and the incomplete answers and the best instruments yet built, and beginning the work again. There is a particular quality to the night sky that only becomes visible when you have spent some time thinking about what is out there. On a clear night, away from city lights, the sky is not just beautiful, it is layered. The nearest stars are a few light years away. The Andromeda galaxy, visible to the naked eye as a faint smudge, is 2.5 million light years away. The light reaching your eyes from it left before modern humans existed as a species. The faint background glow of distant galaxies, invisible without instruments, stretches back billions of years. And somewhere in that glow, a fast radio burst is arriving right now. Not visible to your eyes, but arriving, passing through the atmosphere, passing through the walls of whatever building you are in, passing through you, moving at the speed of light, carrying whatever information it carries about the thing that produced it, continuing on its way. These things are passing through us all the time. Cosmic rays, neutrinos from the sun, billions per second through every square centimeter of your body. The CMB, warming the universe to its 2.7 degrees from every direction. The light of 1,000 undetected events. We are bathed in the universe. We are immersed in it. We are made of it, in the most literal sense. Every atom in your body was forged in the interior of a star that no longer exists. The carbon in your cells, the oxygen in your blood, the iron in your hemoglobin, all of it was produced in stellar nucleosynthesis, in the nuclear furnaces of stars that lived and died before the sun was born. You are not separate from the thing that contains the Great Attractor and the cold spot and the trajectory of Oumuamua. You are part of it, a small and temporary and conscious part of it, which is perhaps the strangest fact of all. The scientists who spend their lives on these questions are not escaping the world. They are not retreating into abstraction. They are looking at the world, at the real physical world in its largest form, at the actual properties of the actual universe that contains everything that has ever happened or ever will happen. The person who studies the cold spot in the CMB is not doing something remote from ordinary life. They are asking the oldest and deepest question there is, which is, what is this place, and how did it come to be the way it is? The same question children ask when they first look up at the night sky and want to know what all of it is. The scientist just has better tools and has learned to be patient with the answer. The patience is the thing, always the patience. The night is very quiet now. Or, if it is not quiet outside, something about this hour makes it feel quiet. The kind of quiet that settles after a certain time, when the world is still, when the small sounds that you did not notice during the day become audible because everything louder has stopped. In that quiet, it is easier to think about the things that are far away. About a star 1,500 light-years distant, dimming slightly, irregularly, in a pattern no one has fully explained. About a point in the southern sky where the oldest light in the universe is slightly colder than everything around it. About the direction of Centaurus and Norma, where through the dust and gas of the Milky Way, a massive concentration of matter is pulling our galaxy toward it with an imperceptible but continuous force. And about that 72-second signal, sitting in a data file from 1977, the numbers climbing to their peak and then descending. The handwritten note in the margin. None of it is here. All of it is there. Out in the universe that surrounds this room, surrounding this planet, surrounding this moment. And the moment is fine. The moment is quiet and still, and there is nothing required of it except to be itself, which it is doing very well. The universe does not need us to understand it. It was producing fast radio bursts billions of years before anything existed that could detect them. It was doing whatever it did to make the cold spot before there was a Milky Way. It was doing whatever made Oumuamua and sent it across the interstellar dark long before a telescope in Hawaii could spot its wrong velocity. But we need to understand it, or at least we want to, which is perhaps the same thing. The wanting is biological, cultural, fundamental. It goes back as far as we can see. Every civilization that left records left some record of looking at the sky and wondering. The wanting predates the instruments by as long as the instruments predate the answers. We have always been doing this. Looking up, wondering, reaching toward the edge of what can be known, finding that the edge moves, finding that behind it is more unknown, and continuing anyway. That continuance is not futile. It is not Sisyphean. Every generation that reaches the edge of knowledge and finds it has moved further has also left behind, for the next generation, a record of what they found. The archive, the data, the carefully written papers, and the annotated printouts, and the observations logged in the dead of night by patient people who knew they might not live to see what the data eventually revealed. That is the gift, not the answer, which may not come in any one person's lifetime, but the careful accumulation of real things, truly observed and honestly recorded. The refusal to invent an explanation just because an explanation is comfortable. The insistence on staying with the open question until the open question closes, even if the closing takes longer than any one life. Tonight, as you rest, something is happening in the direction of Boyajian's star. The star is doing what it does. The light from it, carrying information about the current state of its dimming or brightening, is traveling toward us at 300,000 kilometers per second. But it has 1,500 light-years to cover. The light that left it tonight will not arrive at Earth for 1,500 years. The light that is arriving tonight, that telescopes around the world are collecting right now, left that star roughly 1,500 years ago, around the 6th century, before printing, before the telescope, before anyone had any concept of what a star actually is. The star was dimming or brightening or doing something else entirely in the 6th century, and only now is that information reaching us. We read the old news and call it current observation. All of astronomy is like this. Everything we observe is history. The universe we see is not the universe that exists. It is the universe that existed, at various distances and therefore various times, all seen simultaneously. A layered composite of moments from different eras, resolved into a single view by the fact that light from all of them happens to be arriving here, now, together. The universe we can see is a time machine in every direction. Looking out is looking back. And somewhere in the back of all that history, in the oldest light, in the CMB, is the cold spot. Showing up in the data from every direction you observe it, colder than its surroundings by 70 microkelvins. 1.8 billion light-years across. Patient as anything has ever been patient. The supervoid, if that is what caused it, formed over billions of years. Matter drifted away from that region, or never accumulated there, leaving a volume of space somewhat emptier than average. The CMB light passing through it lost a tiny amount of energy on the way. And the map we made of that light, with our satellites, shows the mark. Or it is something else. Or it is both. Or it is neither. And there is an explanation that nobody has thought of yet. The cold spot does not care which explanation is correct. It is what it is. 14 billion years old, roughly speaking. Unchanged by our interest or our confusion. Just there, in the data, waiting with the infinite patience of something that has been waiting since before the Earth existed. There is a word that comes up often in the writing of scientists who study these things. The word is curious. Not excited, not thrilled, not disturbed. Curious. It is a gentle word for a gentle state. The state of wanting to know without demanding to know. The state of finding something interesting without needing it to resolve quickly. The researchers who have spent years with Boyajian's star are curious about it. The cosmologists who study the cold spot are curious about it. Even Avi Loeb, whose position on Oumuamua is more forceful than most of his colleagues would prefer, describes himself fundamentally as curious. Curious about what it was. Curious about whether we are alone. Curious about the implications of a universe that might be more populated than our models assume. Curiosity is a state you can carry lightly. It does not press. It does not demand. It simply notices and wants to understand, and is willing to wait. The night is doing what nights do. Getting quieter, or it feels that way. The sounds becoming slower. The breath becoming slower. The Milky Way is overhead if the sky is clear enough to see it. 100,000 light-years across. 200 to 400 billion stars. And our little solar system, one unremarkable star among all of those, is somewhere roughly 2/3 of the way from the center to the edge, in one of the spiral arms, orbiting the galactic center once every 225 million years. We have been orbiting the galactic center since before the dinosaurs. The solar system has completed about 20 orbits in its lifetime. Each orbit, 225 million years. And in that time, all of this has happened. Life, extinction events, continents drifting, the slow accumulation of complexity. And at the end of it, or rather at one particular point in it, a species that can build radio telescopes and send them signals it has intercepted and call the 72-second event the wow signal, and wonder whether anything sent it. Oumuamua is still moving. Right now, at this moment. It is somewhere in the darkness between the stars, moving at about 26 kilometers per second relative to the Sun. Tumbling, probably, still rotating in its irregular way. Catching the light of the Sun, which is already too faint to provide measurable radiation pressure. Just moving. If it is natural, it does not know it passed through our solar system. It does not know it was observed. It is not a subject with a perspective. It is a thing, moving through space, subject to physics, indifferent. If it is something else, the same applies. If it is a piece of technology, a relic of some process elsewhere, it is not aware of the debate it caused. It is moving. That is all. Whatever it was, it is unchanged by being observed, by being discussed, by being named, by having papers written about it and arguments conducted over it, and a book published speculating on what it might be. It is just out there, tumbling through the dark between the stars, as it has been tumbling for however many hundreds of thousands of years it has existed. The universe does not acknowledge us, and that is fine. That is, actually, precisely fine. Because the acknowledgement goes the other way. We acknowledge the universe. We notice it. We measure it. We write down what we find and argue about what it means and build better instruments to look more carefully and try again. The attention is ours. We bring it to the universe. The universe does not bring it to us. And that direction of attention, outward, curious, patient, careful, is one of the quietest and most extraordinary things about being whatever we are. The signal gets fainter as you go further from the source. Not because the signal weakens exactly, but because it spreads. Light and radio waves travel in all directions from their source, and as the distance increases, the same amount of energy is spread over a larger and larger sphere. The energy per unit area decreases with the square of the distance, so something twice as far away delivers 1/4 the signal strength. Something 10 times as far delivers 1/100th. By the time a fast radio burst from 3 billion light-years away reaches a radio telescope on Earth, it has spread over a sphere 3 billion light-years in radius. The tiny fraction of that energy that falls on the collecting area of the telescope is almost inconceivably small. And yet it is enough. The instruments are sensitive enough to catch it, to pull it out of the noise, to recognize it as real. There is something beautiful in that. The universe sending enormous energy in all directions, and us, tiny, at a great distance, catching just enough to know it happened. The wow signal, if it was a signal, was sent to a sphere that would now extend 47 light-years in radius from wherever it originated. In that sphere, if the source was transmitting toward no particular target, the signal has been spreading for 47 years, getting fainter and fainter as it disperses. By now, whatever reached Earth in 1977 is a ghost of itself, still traveling, still spreading, carrying still less energy per unit area with every passing year. If there is anyone else in the universe in a position to detect it, they would need extraordinary sensitivity. Or maybe it was directed. Maybe it was a beam, pointed deliberately, the way our own high-power radar transmissions are beamed rather than broadcast. In that case, the signal might still be coherent and detectable in its target direction. But we do not know if we were the target. We do not know if there was a target. We know 72 seconds. We know the frequency. We know the profile. We know the silence since. The silence since. 47 years of silence is not very long in astronomical terms. It is not very long in the life of a civilization. If something sent the wow signal and has been sending it continuously since then, the direction and frequency might have been changed since, or the power reduced, or the technology altered, or any of countless other things. If something sent the wow signal once and not again, there are reasons that would make sense. A brief window of transmission, a test, an event that produced a radio burst as a byproduct of something else entirely. A civilization that has since changed its methods of communication in ways that do not reach us. Or no one sent it. Or someone did and has not sent another. All of these remain possible. The silence does not distinguish between them. The work of the scientists studying these things is sometimes described as searching for needles in haystacks. But I am not sure that is quite right. A needle in a haystack has a definite location. It is there, waiting to be found. The search will succeed eventually if you are thorough enough. The things we are looking for do not necessarily have definite locations. The explanation for Oumuamua's acceleration might not be findable with current instruments. The source of the wow signal might not be detectable by any telescope we can build in any reasonable time frame. The cause of the cold spot might require theoretical advances we have not yet made. The full mapping of what constitutes the Great Attractor might require surveys that will take decades. It is more like searching for a pattern. You look, you gather data, you build models. The pattern either emerges or it does not. And if it does not, you gather more data and build better models and look again. And sometimes the pattern emerges in a way you did not expect, in data you were not specifically looking at, noticed by someone doing something else. The Lorimer burst found in archival data. Oumuamua noticed during a routine sky survey. The cold spot found during systematic analysis of CMB maps made for other purposes. The unexpected finding is a staple of science. Something like a third of the major discoveries in astronomy in the last century were not what the researchers were looking for when they found them. They were looking for something else, or they were doing routine work, and something strange showed up. Which means the next unexpected thing is already out there, waiting in some dataset, or waiting to be observed by some telescope pointed in the right direction at the right time. Already real, already having happened, just not yet found. The room is very quiet. Your breathing is probably slow by now, or it should be. This is a good hour for slow breathing, for letting the day go and the next day not yet come, and sitting in the space between. In that space, the universe is exactly as strange as it always is. The fast radio bursts are arriving. Oumuamua is moving between the stars. The cold spot is in the CMB. The Great Attractor is pulling. Boyajian's star is doing whatever it is doing tonight, and the light carrying that information will not reach us for 1,500 years. None of it requires anything from you. It is all just happening, out there, in the patient dark. And you are here, in the quiet. And the quiet is real. The scientists will be back at their desks tomorrow, or tonight, if they are on different continents, different time zones. Someone right now is processing data from a radio telescope array. Someone is writing a paper about the latest analysis of KIC 846-2852's light curve. Someone is running a simulation of galaxy motions in the region of the Great Attractor, adjusting parameters, checking whether the model predicts the observed bulk flow. Someone is looking at the coordinates associated with the wow signal, probably not expecting anything, just looking. That is most of what science is. Looking without expecting. Measuring without assuming. Recording without interpreting too quickly. And waiting with patience for the universe to show you what it is. And what it is this. Old, vast, mostly explicable, partly not. Full of things that move according to known laws, and a few things that seem to move in ways the known laws do not quite account for. Full of signals that fit known patterns, and a few signals that do not quite fit. Full of structures that match the standard model of cosmology, and at least one region, 1.8 billion light-years across, that is slightly too cold. This is not a broken universe. This is a universe at the edge of our understanding. The edge is not a flaw. The edge is where the understanding ends and the next question begins. And it is a beautiful edge. Not because the unknown is romantic, not because mystery is inherently preferable to knowledge, but because the edge means there is more. More to find, more to understand, more patience to practice, more data to gather, more nights at the telescope, more days at the desk, more papers written carefully and argued over honestly. The universe is not finished being understood. It has not finished showing us what it contains. Somewhere between here and the stars, in the zone we call interstellar space, Oumuamua moves in the dark, whether it is stone or ice or something else. Whether it was born from a star or built somewhere, it moves. The wow signal travels, if it was a signal, spreading, fading, still technically present in the universe, encoded in the electromagnetic field, dispersing toward whatever it is dispersing toward. The cold spot is there. The Great Attractor pulls. Boyajian's star dims, brightens, dims again. And somewhere, in a radio telescope's data buffer, a millisecond of extraordinary energy is waiting to be noticed. The signals get quieter. The distances get larger. The questions stay open. And that is all right. That is, somehow, exactly all right. The universe is larger than the understanding. It has always been larger. It will always be larger than. Good night.